I need one of those things for as many times I've recorded this. This is my presentation for GPS time series analysis for Geology 679, Python for Earth Sciences. This project slash presentation is also what my thesis is about and the ongoing efforts in that arena. One of the motivations was that, well, one, I find the topic interesting, and I wrote a paper in undergrad regarding this research as just a broad overview. But also, this is kind of on the precipice of geodesy and what is kind of moving that field of study forward. And it's kind of on the edge of the capabilities of current GPS computations in terms of spatial resolution, which we'll talk a little bit about later. Uh, Currently, where I'm at in my research is confirming the existence of this anomaly between 2001 and 2006, and more specifically, the peak amplitude is present between 2003 and 2004. After that, it's the attempt will be to attribute this deformation to core mantle dynamics. All the data here that I've used and processed so far is from the Nevada Geodetic Laboratory, or the NGL. It's kind of hard to see that URL down at the bottom, but shout out to the NGL. Here's a flow chart of a pretty standard practice for processing time series data to a point where we can start making assertions and theories about what we're looking at. I've pointed out a few things that I've implemented and used. Like I said, the NGL is where I get my GPS time series data. To remove outliers, there's a lot of different methods, but I found one that worked well, and this is it's density-based local outliers, which is it's a clustering algorithm, which was cool because it came back that we discussed in class. And so I thought that was really neat to be able to tie those two things together. For signal analysis and estimating seasonality within our GPS trends, I used a standard linear trajectory model and a best fit least squares component, which we'll talk about in a minute. There's many trajectory models. The NGL specifically uses something called MIDAS, which you could read a paper on if you want, but I didn't. I didn't utilize that. I just used a least squares fit because it worked just as well for what I was doing. A common mode filter, or a common mode error analysis. This was something that Cornet Kramer and Jeff Blewett have published a paper on recently, and so I used Cornet's Fortran program for this part of my analysis. I'm not planning on touching that and rewriting that in any other language because it's a very robust and large program that does many things. And I have white noise, flicker noise, and random noise here. And that kind of signal analysis is separate from seasonal signal analysis. Seasonal signal analysis is actually a physical deformation of the solid Earth, while white, flicker, and random walk noise are present from computations and just from it being a digital signal. So that's it's just a separate noise that we consider. Um, so part of Cornet's script was a spherical triangulation Delani, but I didn't know what that was originally, and so I wrote a different Python script purely just for visualization of the spherical triangulation, and I overlaid a heat map to see the average distance between these stations. And just briefly, a Delaunay triangulation tries to create as equilateral as possible of a triangle between stations without any intersecting or overlapping points outside of the 3 points that compose a triangle. And that's just a really rough definition. So moving on to the standard linear trajectory model, or SLTM, and the best fit line. This seasonality can be modeled by the formula above, which takes a positional vector y and its velocity at time t, um, and that's just the equation of a line, right? And which I have down here, which for some reason I switched it to x instead of y. Um, but then, in order to model the seasonality of this line, we can take the sine and cosine aspect and modify it such that it will estimate the seasonality trend. We use 2 pi for our annual seasonality, 4 pi for our semi-annual seasonality. And since it's a linear system, since it's a system of equations, we can model any system of equations as matrices, and then we can perform some linear algebra. We have our D equals GM here, which is a well-known uh, uh, formula or uh, equation, and you'll see the results here. These are the plots, and in GPS, there's 3 components. We have east, we have north, and we have vertical. Some people prefer to call the vertical up, but I like to call it vertical because when I think up, I think north. So I use east, north, and vertical. And as you can see, the east observed, north observed, and vertical observed are the unaltered, unfiltered for the most part, GPS times. And when I say mostly, there are some there is some filtering that has to be done as the signal is processed originally for like atmospheric loading and tidal forces and like the overall flexure and deformation of the Earth. Um, yeah, but overall these are unfiltered components and with the fitted seasonality line to them, which is much easier to see on this vertical component and the north component here. And if you notice on the y-axis, the scale for the observed is different than the residual. Now to get the residual, I subtract this fitted line from the observed, and then that will leave me the residual here, which you can see now the median value is hovering around 0, which is what we want. And then this is what we will use for further analysis. And here you can see there is a bit of a bump in the eastward component, not much of anything in the north, which is expected, and then a larger noticeable bump in the vertical residual, which is what we were expecting and what we're looking for. Next was to plot all the GPS stations, which I believe in here there's 371 individual stations, and I plotted each data value for each epoch here to see if we could see any kind of variation, and we can. In the residual position in 2001, you can see that it's mostly zeros and negative values. And then as we move to 2004, when the peak amplitude should be present, there is a shift to positive values. And again, this isn't taking into account the direction. This is simply just the amplitude of the values here. And then residual for the east, and basically 2006, the start of 2006, the very last day of 2005, we see it subsides and we get 0 and close to 0 values. And this pattern is present in the other 2 components as well. Obviously not as significant in the northing because the anomaly isn't necessarily present in the north component, but it's still present. And then in the vertical, it is fairly pronounced, where you can see in 2001 zeros and negatives, a little bit of a positive over here. But then in 2004, you can see a shift in the scale here and positive values propagating westward. Well, yeah, propagating westward on the map, but the actual displacement vertical here. And then this subsides again last day of 2005, where everything settles, where the anomaly has essentially passed. The next logical step was to now iterate through every single time step that I have for the stations and put them together as an animation to see if we could visualize the flow better. Now here it's just it looks like uh, glitter is being thrown all over the station, so there is some more processing to do to create a more smooth animation, and that also comes back down to utilizing Cornet's um, uh, common mode filtering script, which also outputs various grids that have been smoothed. Um, but I have a separate issue with getting that to plot the same way as this, but that's something separate. Here is it's a despeckled and spatially correlated with 50% weighted median between stations, and this is more in line with what I want my final visualization to look like. So up here, I controlled a trimmed maximum between the stations at 2 sigma values. Um, and here was no trim maximum. I used the entire extent of the filtering. And you can see there's a bit of a difference and a difference in distribution of values, which for whatever reason got cut off when I tried to save these images. But this should say, this should be negative, no, this should be, yeah, -7 here, +7 here, and the scale is in millimeters. Um, so I need to figure out why that didn't save correctly, and further, I need to create animation from this. Uh, Overall, even though this processing is still a work in progress, I think it shows, and I think it's fair to say that there is evidence for an anomalous bump occurring between 2001 and 2006, specifically the peak amplitude occurring between 2003 and 2004. As shown, there's a much stronger presence in the anti-east component, aka the westward component, and the vertical component of the GPS signal. Certain things to take note of is that the GPS currently has a very high accuracy and precision in the horizontal plane. For example, computational accuracy for the longitudinal component is 1 nanometer for near Earth locations, and that you can read about that if you want to read Jeff Blewett's recently published paper. I can't quite wrap my head around it. Currently, it's super math heavy, but it's an interesting read. As a general rule, the vertical accuracy as a common guideline can be 3 times larger than that of a horizontal component, um, though that was just expressed as a general guideline by Blewett, Kramer, and Hammond in a paper they wrote in 2016. I couldn't find an exact number for the vertical resolution of GPS signal, but I do know it is less than that of the horizontal component. And to conclude and acknowledge, I know that my thesis, and I'm aware that my thesis is still very much in its infancy, and I have a lot to read and learn and attempt to understand, and then hopefully I can start piecing some parts of this together and make sense of some of it. The next thing, because I am nearing the conclusion of this anomaly confirmation, is maybe understand or read about if we're assuming that this anomaly originates from core mantle boundary dynamics, is that there is a geomagnetic waveform that travels at higher latitudes and does propagate westward. And this westward propagation does line up fairly well with the time span we're looking at in the western United States. I'll see if I can get it to play here real quick. So right around here, you could see that, yeah, it's positive, and then you could see the negative acceleration here. Um, so that concludes my presentation, and that is all I have. Thank you for everything, and